So we're very pleased today to be joined, albeit virtually, by Professor Amina Helmi, who's a very distinguished dynamicist, astrophysicist, and particularly an expert on the Milky Way, as well as in many other things. She's worked on stellar streams, on the galactic halo, on dark matter, on chemical tagging of stars in the Milky Way, and so on. She's been a permanent faculty member at the Captain Institute in Groningen since 2003, and she's had a bunch of distinguished students, one of whom is Helmer Koppelman, who is currently not here. He's stuck in the Netherlands, which is the reason you're listening to me and not to him. I won't go through all of the awards and distinguished lectures and so on that Amina has had, but she is, for instance, just in the last few years, been awarded the Division of Dynamical Astronomy's Brewer Award, the prestigious Spinoza Award, and my favorite is she is a Knight of the Order of the Dutch Lion. I'm not sure what that means, but it sounds fantastic. And this is probably not a coincidence. I mean, she has many, many influential papers, but in the last few years, she's of course been key in the dissection of the data from Gaia. And she wrote a paper along with Helmer and several others in 2018 on the discovery of what they call the Enceladus, which is basically a small galaxy that fell into the Milky Way several billion years ago and formed much of what is now the galactic halo, the stellar halo. And as of this morning, that had 524 citations in 3 years. It's probably even gone up since then. So that's enough from me. Without further ado, Professor Amina Helmi will tell us about new views on the Milky Way.
Thank you very much. And thank you also for the invitation, for the introduction, very kind introduction. And it's really a pleasure and an honor to be here, to be sharing with you some of the discoveries we've made and some of the lessons we've learned over the past few years, mostly indeed thanks to the Gaia mission. So I wanted today to focus on new views on the Milky Way and in particular to discuss mostly its early history. So what we have learned in recent years and are still learning about the early days of our galaxy. But before I do that, I also want to thank my collaborators. Particularly, I want to thank the DPAC Consortium, the Data Processing and Analysis Consortium of the Gaia mission, all of the 500 astronomers and engineers that are spread out through Europe that are producing these amazing data sets that we love so much, under the leadership of Anthony Brown, particular collaborators within DPAC in the work that I'll present today are Karim Babusier as well, and from my group, a few postdocs, Jovan Veljanovsky and Martin Bredos have played a major role, Davide Massari as well. And in recent years, there's also contributions from past members such as Helmer Koppelman, who's still working with us, and current members such as Tadafumi Matsuno, Thomas Rislara, Sophie Lovda, and Emma Dodd, all of whom have contributed to the work that I'll be presenting today. So big thanks to them, because without them, we wouldn't have been able to do the amazing science we've been doing. Right, so you all know Gaia was launched probably at the end of 2013, and it has been scanning the sky since then. And as it scans the sky, it measures the positions very accurately of the stars. And by doing this repeatedly, it actually measures how they move on the sky because of their intrinsic motion, so the proper motions, but also because of their parallax, so which gives us an estimate of their distances. Gaia also provides color information for the different stars, and this has been done for a data set that now encompasses somewhere between 1.5 and 1.8 billion sources. For a subset of these stars, we also have spectroscopy. We have radial velocities in particular. So it's a small number, it's 7 million sources for now. We expect in the next years that this will increase to 200 million sources, roughly. But for now, this is the information that we have. And this is really impressive, an impressive data set that is really changing the field in many different ways. And it's, being part of DPAC is quite, one has quite a sense of pride for Gaia because of the impact it has in astrophysics. So you see here some numbers. It's just, mind-blowing to see the vastness of this data set. And such vastness, what it really implies is that you can really do a lot of different science. And that science goes from studying solar system objects all the way to studying the distant quasars. In particular, our group has, in recent years, has looked at the dynamics of the Milky Way disk and discovered evidence that even in the solar vicinity, the Milky Way is still evolving. It's not a system in dynamical equilibrium. It's of course not in isolation, and we can see that in the detailed motions of nearby stars in the disk. We've also measured the motions of stars in the stars of globular clusters, and using globular clusters, one can obtain an estimate or estimates of the mass of the Milky Way. We've also worked on this, and we've also combined Gaia with HST to obtain to try to measure and have measured the proper motions of stars inside a few dwarf galaxies around the Milky Way. And so that's quite amazing, because then you get the three-dimensional motions of these stars in these tiny dwarf galaxies that are dark matter dominated. And so we've been able to constrain a bit more what is the dark matter distribution in these objects. So you can see the breadth of the science that Gaia gives you. But really the question that Gaia was meant to address is, how did our galaxy come to be the way it is? What is its history? So if we think about the Milky Way, and you see this beautiful picture from Gaia, what we know is you have a central bulge, you have a thin disk, a thick disk component. So in the thin disk, stars are still forming. You have a thick disk component, and there's a stellar halo. And the stars in each one of these components have different properties. So it's not only that the spatial distribution is different, but also the kinematics of the stars are different. So for example, stars in the disk are mostly moving very orderly on circular orbits around the galactic center, whereas stars in the stellar halo move on rather elongated orbits, say around the galactic center. What you also see is differences in the populations. So stars, as I said, stars in the thin disk, there are stars still forming today, while stars in the stellar halo, there are stars that are as old as the universe itself, as far as we can tell, right? So these halo stars have basically witnessed how the Milky Way was put together. And so in principle could be used to unravel the sequence of events that led to the formation of the galaxy as we see it. So how can we do this? We do this by doing what we call galactic archaeology, and we use stars as fossils, as it were. So stars, in the way they move, they tell us where they come from. In their ages, tell us when they were born. In the chemical composition, reflects the chemical composition of the medium, the physical conditions of the ISM from which they formed. And so groups of stars with similar chemical composition will have formed in the same environment. If we take one of these cosmological simulations of galaxy formation, and this is what you see here on the left side, is a series of snapshots from one such cosmological simulation from some years ago now. But the basic idea is, shortly after, sometime after the Big Bang, the first galaxies form. They are small, they merge to produce larger and larger systems. And after a while, you produce a system that's significantly, that's relatively big. And what you see, say by the present day, is you see a full galaxy where, say, that has a disk component, most of the stars in the disk will have formed in the disk itself. but the stars that you see in this halo component will actually have been born in these building blocks. And by looking at, say, by studying the properties of this component, then we can make a link between what we see nearby to us and the very distant universe, the very early universe. So some of the questions that we would like to address by looking at these very old stars in the stellar halo are, how important were mergers in the history of our galaxy? When did they happen? What were the properties of these building blocks? And do these building blocks bear any resemblance to the galaxies that we see around us today? So in that context, the stellar halo is really a treasure trove if you are after finding out what was the early history of the galaxy. And as I was saying, the memory of all these merger events can remain in the form of substructures, as you see here. So if you had, so this is from another cosmological simulation from the Aquarius simulation suite. What you see here is what would be the spatial distribution of stars, where the stars are color coding according to which galaxy they formed in, right? So from these building blocks, each building block has a different color, and then you can see, what you then see is that in the outskirts, so at large distances from the galactic center, what you expect is that there should be coherent, spatially coherent substructures. You can see that you would identify substructures just by counting stars on the sky. But in the inner regions, it's really very difficult to see spatially any distinction between the different building blocks, right? Even though the stars still come from different objects. So one of the questions is, how do we tell if the distribution of stars is smooth in space? How do we actually tell that they came on board different galaxies that merged to produce the stellar halo? The inner regions are also particularly interesting because galaxies do form inside out. So when you look towards the inner regions, you're really going further back in time. The outskirts really reflect more recent accretion events only. So how do we find merger debris if we're looking in the inner regions of the galaxy, if we're really going back in time? So this is a small simulation that shows how a small galaxy, here in red, is being disrupted if it orbits in a region that's close to the galactic disk, so in the inner region of the Milky Way. And you can see how the galaxies turn apart because of tidal forces, and how the stars are mixing rather quickly in space. If you look at any location in space, you actually see that the stars are moving together. So even though the spatial distribution is rather mixed, at any given location, the stars maintain memory that they came from another object in the way they move. They move together through space, defining streams. So if we take a snapshot of this simulation, say, and you were to plot the spatial distribution of the stars, and you would look at how the stars would be moving, say, in a small volume around the sun, then you would see, say, one group of stars moving towards the upper right, and one group of stars moving towards the upper left. If you then plot the velocities against each other, then you would have two clumps, right? So two streams, basically. But you can go one step further and say, okay, initially all of these stars were together in a small galaxy they were at the same location in space. They were moving with very similar velocities. And so they had very similar energies and very similar angular momentum. So initially, all of the stars defined a clump in this space of energy and angular momentum. Now, if energy and if angular momentum are conserved quantities, then the stars will, at the end of the day, independently of where they are, still have that same energy and angular momentum. So if you look at a later time, you would still find a clump in this space. So that's the basic idea. If we have the stellar halo built up via mergers from different objects, we can look, but these objects, these stars don't actually come with flags that tell us where they were born. We can look at the velocities and we would find these different moving groups. But if we look at conserved quantities, at integrals of motion, such as energy and angular momentum, then each one of these, say, progenitor galaxies, each one of these building blocks would define a clump in this space, and this clump would be easily distinguishable. You can see that even if I didn't have this, color coding, that a clustering algorithm should be able to detect all of these clumps without much trouble, right? So that's the basic idea. The basic idea is that if we want to have recover the merger history of the Milky Way in the inner regions where most of the stars are, then we should have access to kinematics, 60 information we need. We need both their positions of the stars and their velocities through space to be able to compute these quantities. And we should be able to see a lot of substructures if measures have been important. So this was a prediction that I made some 20 years ago, and it took me roughly 18 years to see, what was there in the data and whether, this idea worked. So I'm going to discuss now what we found with the Gaia data in the halo near the sun. And I'm going to talk about results from that we obtained in the early days of the second data release of Gaia, which is the one that was the first to give us 60 phase space information for all of the stars. And then I'm going to move towards more recent analysis of the latest data release from Gaia. So you see a bit of evolution in the results. So as I said, let's focus in the halo near the sun. And it's really a story of two main characters. To set the scene so that we're all on the same page. So if, say, this is the galactic disk, we have the sun here. I'm going to look in a volume of about 2.5 kpc around the sun. I'm going to look at all of the stars and how they move through space in this volume. And so what we have is, if we think in terms of velocity, we have a velocity in the direction of rotation, v phi or vy, depending on which coordinate system you use. You have a velocity in the plane, in the radial direction, and you have a velocity in the vertical direction. And so most of the stars are in the disk, and so a lot of stars will be moving with very low velocities in r in z, but high velocities in v phi. So let's see what the data showed. So this is a plot that shows the kinematics of stars, again, within 2.5 kpc from the sun. So this axis shows the rotational motion. This axis shows random motions. These are all of the stars for which we have 60 phase space information, good distances, and good velocities. So you see most of the stars near the sun are moving. There's a very dark spot here. That's a very high density of stars. Most of the stars near the sun are moving like the sun with 230 kilometers a second and are in the disk. And as you move away from this, you move in this direction, you're moving into the realm of the thick disk, which is lagging behind the sun, slightly higher random motions. And we thought before Gaia that this region, say beyond this red semicircle, would be the region occupied by stars in the halo, right? So rather large random motions, not much rotation. What did we see? So what we see here are basically this component here, which corresponds to the tail of the thick disk, if you wish. It's just a continuation of this distribution. And then we see this component here. So what's not in this component actually has, this is zero rotation. So quite a fair fraction of the stars have retrograde motions, actually. So that's rather peculiar and was rather surprising to find. Basically, the halo is dominated by two components. This is also what was found when plotting a color absolute magnitude diagram for the same stars. Basically, what you see is two sequences clearly well separated and defined, where this sequence corresponds to the hot thick disk, and this sequence corresponds to the stars in this component. What we then did was to look for chemical abundances for the stars, and we used the apogee survey, and we selected stars located in this region that we call the blob. And what you then find actually is that the stars in this region define a separate sequence from the stars in the thin thick disk and in the thin disk. Now, this separate sequence, this is alpha over iron versus iron. The fact that you have a separate sequence actually tells you immediately that these stars, which form the majority of the stars in the halo, did not form in the Milky Way, but formed elsewhere. So these stars stem from the accretion of an object, of another galaxy. And you can tell from the slope of this sequence, the star formation rate and how massive this object was. And it's roughly something like 6 × 10⁸ solar masses in stars. So that means that a fair fraction of the halo near the sun was formed from the accretion of this one object. You can ask yourself, what did it fall into? And you can ask yourself, when did this happen? So people had measured the ages of stars in this sequence, and in particular those that are more metal rich, and had found that indeed these stars are roughly 10 gigayears old, and that there are stars in the alpha rich sequence, in this sequence, that are even older. So that means that when this object fell in, there was a disk there.
You know, we have a question in the audience.
Yes.
Hi, Amina. Can you tell us how the stars that show up in this plot are selected? In particular, do you have a distance criterion? Is this all stars closer than some certain amount to be included in this plot?
Yeah, so what we have here is a distance quality criterion. So we only allow for distances better than 20, that have errors smaller than 20. And that reduces the sample in such a way that most of the stars here are within, say, 3 kiloparsecs from the sun.
Thank you.
And so what you see, what you see is that the vast majority are on this sequence. You can tell that these stars are younger than the stars that are in the thick disk sequence. And so that tells you that when this object fell in, there was a disk in there. And one can estimate what would have been the mass ratio of these two objects. And that amounts to roughly a mass ratio of 1 to 4. So this is a relatively massive event. This is on the verge of being, say, it's in the transition between minor and major merger. So a significant event. And so that must have led to the formation, to the heating of whatever disk was present at the time. What's interesting is that not only we can infer this, but from the kinematics of the stars, we can actually tell what the merger configuration was. So if we look at the data, this is again the same plot. What you see is this arc that's rather clear in the data set. We had simulation of mergers between a disk and another galaxy of similar mass ratio. And you can compare the kinematics in a similar volume to those in the simulations. And then what you see is that indeed, if you merge with a spheroidal galaxy, then the features, the arcs are less well defined, for example. So you prefer to have disky galaxies. And also the fact that the arc is, on the retrograde side with very negative velocity that means that the encounter was retrograde. And this, say, encounter bears quite a big similarity with, what you find in the data. So basically, what we're seeing is the kind of the linked formation of the stellar halo and the thick disk. So what you see here is that simulation of a disky galaxy on a 30 degrees inclination encounter, and how that leads to both the formation of the stellar halo, formed mostly from stars from Gaia-Enceladus, which is the object, how we named this object. But also you see how this disk is being puffed up because of the merger it's experiencing. And I particularly like the story of how we named this object. So Enceladus is one of the giants in Greek mythology, and this was a relatively massive galaxy. It's buried, it's said to be in the myth, it's actually the son of Gaia and the sky, and it's actually said to be buried under Mount Etna, where it is responsible for seismic activity. And what you see here is indeed that in this simulation, that in fact what Gaia-Enceladus does is it does really lead to quite a bit of heating and activity in the thick disk. So this was really a milestone in galactic history, and probably and the last big merger that the Milky Way experienced. Now, I showed you this simulation and I made a comparison to the simulation, but these simulations are purely embodied. So we have dark matter particles and stellar particles, but we have no star formation. And in fact, if we think that this merger, sorry.
Looks like we have another question in the audience.
Yes.
How do the arcs vary as you vary the mass ratio of the mergers?
So we haven't, in fact, we haven't done a full a study of the impact, but what you see is that the lower the mass ratio, the lesser the impact on the thick disk, the amount of heating. So if you go below something like 5%, it's typically insignificant. The fact that we see this contribution of the heated disk in the kinematics of the halo, so if I go back here, the fact that we see this component in the halo actually means that this is a rather massive object that fell in. If it were more massive, then it would have probably destroyed the disk itself. So it has to be, say, of somewhere between, I would say, 0.15 to 0.3, but not more massive, not more massive than that. And that is coincident with, say, that those are dynamical arguments, but the arguments from the chemical abundances give you also these mass ratios. So I think that there is a consistent story there.
We also have a question on Zoom from Amitabha.
Yes.
Hi, you showed this very nice pictures a little earlier in the talk on conservation relations, but I also have a question to you regarding the oscillations in the ZVZ plane. Can you point to whether you see a persistence of this oscillatory feature in ZVZ?
Yeah, so these features, it's a bit of a complicated question to answer at this point.
So you can postpone it then until the end of your talk, because I don't want.
Yeah, that'd be great. Thank you.
Sure.
I'll get back to that.
Okay, thank you.
Thanks.
Yeah, I just wondered, maybe you said it, when you talk about this part of the stellar halo, what distances are we talking about? How far into the halo do you see this?
Yeah,
stuff?
so this is this analysis is based on stars that are within 2.5 kiloparsecs from the sun. Now these stars go out to in their orbits, they go out to 20 to 30 kiloparsecs. And there is evidence of, say, that there is a number of features that have been observed in the halo associated to breaks that correspond to the pile up of this debris at the apocenter of their orbits. So this object seems to really be dominating, say, the inner 20 to 30 kpc from the sun, from the galactic center.
Good, thank you.
So as I was saying, the simulations I talked about are just collisionless simulations, but we expect, particularly at high redshift, that disks were gas-rich, right? And so an event like this must have likely triggered quite a bit of star formation in the galaxy. So this is some very nice work by Kamer Galar and collaborators, where they again looked at, say, the blue sequence that would correspond to Gaia-Enceladus, the red sequence that would correspond to the disk that was puffed up, and looked also at the region occupied by the canonical thick disk. And what I found was that if you look at the age distribution of the stars in these three components, is that the red and the blue sequence, so Gaia-Enceladus and the heated disk, have similar age distributions, that they basically stopped forming stars around 10 gigayears ago. That's basically when the merger took place. And then what you see is a peak in the age distribution of stars in the canonical thick disk. So if you think about what this means, is that there's something like a sequence of events that Gaia-Enceladus fell in. There was a disk. This disk was puffed up, but because the galaxy was so gas-rich, this event also triggered the formation of the canonical thick disk. So this is really a milestone in galactic history, where different components, as we know them, seem to have been formed. We also see similar events in the Eagle cosmological simulation. So this is one example where you also see this component. You see a heated disk, and you have a normal disk. And so this corresponds, in this particular cosmological simulation, it's a mass ratio of roughly 20%. And what's interesting about this event in these particular simulations is that you really see a global effect on all of the components. You see an increase in the star formation rate in the thick disk, and also you see that the thin disk starts to form more clearly after this merger is completed. So I think in that context, we also have to go, think beyond the stellar halo and try to understand what the impact of this event has been, even on the thin disk, but even perhaps also on the formation of the galactic bar and bulge. So what I showed you basically is this one big fish, right? That's different because of the chemistry that moves in a different way as the majority of the stars in our galaxy. But do we have evidence of other substructures in the halo near the sun? And so this is where we actually decided to go for a full clustering algorithm to identify these substructures. And now we're using data from the latest data release from Gaia. And what I'm plotting here is, again, these integrals of motion, so energy, Z component of the angular momentum, another component of the angular momentum that is so perpendicular, and the circularity of the orbit. And so what we decided is to apply a clustering algorithm on this 4-dimensional space, and we selected an algorithm that doesn't use any scale, and that's a single linkage algorithm. It simply measures the distances between the stars in this 4-dimensional space. So every star is in a cluster, and then what you do is you build a tree hierarchically. So if you have a data set, you just compute the distances between the stars. So you link these two, then the next pair that is linked is 1 and 2, right? So 1 and 2 are at a slightly larger distance, then 3 and 4 are linked, then these two are linked together, then they're linked to this one, then to this one, and then finally to 8. And so the whole thing is linked. Now the question is, now that you have these clusters, at which level or how do we actually determine that these are significant? And so to do that, what we do is we compare to a random data set, and a random data set is simply a data set that has the same spatial distribution, but where the velocities have been reshuffled. And you can immediately see that substructures that are apparent, such as, Gaia-Enceladus here, basically disappear in this random set because we are reshuffling the velocities. And so what we do is we run the algorithm, we identify all possible clusters, we fit an ellipsoid in 4D to these clusters, we count how many stars there are in the data and how many stars that are expected from these random sets. And in that way, we identify the regions that contain an excess of stars compared to the random sets, and we select the clusters at the point in which they reach the maximum significance. So because clusters get bigger and bigger as you get more stars, but if you are basically going outside of a true cluster, then all you add is noise, and so their significance becomes lower. So at the peak significance is where we identify the different clusters. And this leads us, in the case of Gaia EDR3, this led us to the identification of 83 different clusters. Now, this is a large number. We were not expecting to find so many clusters. Roughly 20% of our data set is in a cluster, and the median size of each cluster is about 40. And you can see the distribution of the clusters in the various subspaces here. And one of the things you notice from this is how fragmented these clusters are, right? So the region occupied by Gaia-Enceladus is formed by 30 different objects. There's an overdensity here. There's also 5 different objects. So we can't stop here if we're really trying to understand what this is. So the clustering algorithm as is, just this output doesn't tell us the full story. We need to take this a step further. So to do that, what we do is we look at the structure, this hierarchical tree that we are constructing on the basis of the distances. And what we define is what we call the Mahalanobis distance, which is, we use that ellipsoid, this the kind of the PCA in 4D, that is our covariance matrix, and we calculate what is the distance from between any two clusters in this 4-dimensional space. And so this allows us to establish a relation between the clusters, how far they are in intervals of motion, but it also allows us to establish in a robust way a membership probability for the stars, which is interesting if we want to do follow-up, for example, to get chemical abundances. And so this is the hierarchical tree, the dendrogram that we can construct on the basis of the clusters identified. And one of the things you notice is, something like 7, 8 large big clusters and a rather large complexity, such as this cluster F. So I'm going to take you through what this implies step by step. So what do we do with this? But before I do that, what you can do is you can look at where these, say, different large groups are located in, say, energy and angular momentum. And so, for example, this big cluster is, of course, Gaia-Enceladus. Then there's another cluster here, and a few other clusters, some in the region occupied by the hot thick disk. And some of the clusters are really, really tiny, like these ones. And it turns out these clusters have extremely low velocity dispersions, and sometimes they have very small spread in metallicities. So this could imply that some of these clusters could be disrupted star clusters in the halo. that we are now detecting. So that's something for follow-up that is particularly interesting. What's also interesting is that what we're finding is consistent with previous work, previous reports of building blocks in the halo based on Gaia DR2. So the regions where we are finding overdensities are similar to the regions where other people have found overdensities. Nobody so far have found so many of these clusters. So we have, as I said, have to take this one step further. So to take this one step further, what we want to do is to identify really these building blocks. What we want to do is a quantitative comparison of the different clusters, particularly if they are close by in integrals of motion space, in terms of, say, the metallicity distribution, in terms of the stellar populations. So let me give you an example. So this is one of the clusters. This is, say, one of the structures identified, 2 clusters. This is where they lie in energy and angular momentum. This corresponds, actually, it's a known cluster. It corresponds, a known region. It corresponds to the Helmi streams I discovered many years ago. What we then do is we look at the distribution of stars in color and absolute magnitude. We fit a single isochrone to all of the stars in this group. And we look at the distribution of colors. We ask ourselves, are they consistent by means of KS test? And we also look at the metallicity distribution and ask, are they consistent? They are consistent with being from the same progenitor. So we merge these two into a single unit. And so I can walk you through this dendrogram. We've done this for all of the structures. So for example, this is group E. It's here. It's also a known region. You find 6 different clusters. What you see kinematically is that all of the green ones are indeed rather similar, that the blue one is very compact, and that the red one has different kinematics. So on the basis of, say, the kinematics, you would separate these clusters into 3 different objects. If you look at, say, the metallicity distribution, it's clear that this cluster in blue is different, right? So what this compares is the pairwise comparison between the different clusters identified. So from here we say, okay, we have 3 different objects. Here's another one formed by another region, also known region where an overdensity had been claimed before. What you see from the KS test is really 2 groups. So these 2 clusters could be linked, these 3 clusters could be linked. And so that produces 2 structures that are well separated also in integrals of motion. And you can see how the metallicity, so the distribution functions of the 2 clusters are different. Similarly, you have Gaia-Enceladus, 32 significant clusters. You can see again, Gaia-Enceladus, how dominant it is. It basically has the metallicity distribution function that we use to associate to the stellar halo. And what's interesting is that if we look at the chemical abundances of these stars, we can clearly see now during a purely dynamical selection from this clustering algorithm, how they follow a very nice sequence, and how the stars in Gaia-Enceladus, this is particularly interesting, have a rather low magnesium over iron, even at low metallicity compared to other stars at low metallicity. So our final set of substructures, so we reduced, so we kind of ran through this dendrogram and merge clusters if they have consistent stellar population. That leads us to a final set of 11 large objects and 7 independent tight clusters, where we think this may be disrupted star clusters. What's interesting is that if you now compare all of these objects, and you see their distribution here in angular momentum and energy, if you compare their, for example, metallicity distribution functions to one another, then you indeed see that basically you're only populating the diagonal of this matrix. So these are real, these clusters, these say, substructures, these are really distinct from one another, right? So that also is, an interesting result from this analysis and provides support for the idea of the procedure that we're following. What you see from the metallicity distributions is that some clusters are very metal poor, relatively metal poor. Some clusters seem to follow the thick disk. And some, like this one, this is cluster D, seems to have a mix of populations with some thick disk and some perhaps in situ or early accreted event. Similarly, we can do the same thing and fit again isochrones to each one of the substructures. We also see how they are different from each other. And we can also do the same for the chemistry. Although not many stars have chemical abundances, and so we're really keen on getting large samples of stars with chemical abundances so we can really probe the histories. But what you see is that even with a few objects per substructure, you see that the trends for the different groups are different. So it's suggestive, it's not fully significant, but it definitely supports our analysis. So with all of this information, what we decided to do is to take a global view at the stellar halo now. And so what I'm plotting here is all of these substructures, these 11 big objects and the small ones. And I color-coded by the average age of the structure. And same here on the right panels by the average metallicity. And so one of the things you notice from this is that if you look at the age, the oldest structures tend to be on retrograde orbits. Structures on prograde orbits tend to be younger. Similarly, metal poor structures tend to be on retrograde orbits. Metal rich structures tend to be more on prograde orbits. Now that there has been known for a while, even from Segway and SDSS, that the outer halo seems to be more metal poor and retrograde. We are sort of seeing this also for the inner halo. But what's curious, and we still don't understand, is why these structures that are on retrograde orbits would be older on average. Is it because prograde structures fall in later? Or is it perhaps because structures are falling in groups? So this is an open question that I think would be interesting to address by looking at cosmological simulations. What's also interesting is that we can also associate to these different building blocks globular clusters just by plotting their positions, again in energy and angular momentum. And one can associate it to the different building blocks. And it looks like something like 50% of all globulars have been accreted. What's interesting is that you can also make age metallicity, plot their age metallicity relation. And what you actually see is that each one of the clusters associated to each one of these big building blocks tend to follow a different age metallicity relation that is consistent with the estimated age of the progenitor galaxy, estimated mass. Right, so we now have a sketch of a merger tree of the Milky Way. And this was based on the analysis of Gaia-DR2, so this needs to be updated with the new objects that we have identified. But we're really beginning to unravel how this merger tree of the Milky Way looked like. So with that, I'd like to bring my summary. So I think Gaia, supplemented by these ground-based surveys, particularly those providing chemistry, are really truly causing a revolution in the field of galactic archaeology. We've discovered that the halo near the sun is largely the result of the accretion of one massive galaxy that was similar in its early days to the Large Magellanic Clouds. that this galaxy, Gaia-Enceladus, heated an ancient disk, and that led to the formation of a thick disk. And here I want to stress the importance of combining kinematics, the photometry, and the chemical abundances. And so also the importance of new instruments that are coming up that will measure with high resolution the abundances of large samples of stars. From the analysis of the R3, we've identified 11 large substructures that are associated likely to accretion events, but also we are finding also substructure in that early heated disk. This puzzle, that the fact that the substructures on retrograde orbits seem to be older, that's something that we have to try to understand. And I think the next step is particularly exciting because the characterization of all of these substructures, so determining how large they were, determining perhaps even their IMF, star formation history, that gives us a link to what happened in the early days, maybe to the first stars, maybe some of these building blocks were responsible for ionization in the local universe. But to really make use of this and try to understand how all this happened requires a holistic approach. We not only need new data releases from Gaia, we also need high resolution spectroscopic follow-up and the help of simulations. And I think it's amazing times to make a link between the high redshift universe and using nearby stars. So thank you very much for your attention. I'll stop here.
Okay, so we have time for questions. The first one I think was from Elliot on Zoom.
Thank you. That was a fascinating talk. I had a question about the thick disk. So there's some evidence from simulations and less directly from observations that some of the thick disk is a consequence of star formation being in more turbulent and hence thicker disks in the past. So I wonder if you can just comment on that sort of in situ mechanism versus the external merger heating origin of the thick.
So thanks for the question. That's very valid. So I think both things are happening, or have happened in the case of the Milky Way. So that there was a disk there at the time of the merger, I think that is that's clearly there, can really be established from the ages of the stars, right? So we know there was a disk. We don't know how thick it was to begin with at redshift 2. We don't yet have enough constraints on that. We know perhaps we can reverse engineering to do some reverse engineering to try to figure out how that disk was. And then what we know is also from the ages of the stars that this event triggered a lot of star formation and that those stars are in a thick disk. Now, whether that is the medium that was, I guess it's a mix of the medium being turbulent, but also the fact that there was an ongoing merger at the time that led to a thick disk being formed. It's a bit hard to say, what is dominant, but these things were happening at the same time, I would say.
Thank you.
I can't keep track of all this, so I'm going to alternate back and forth between the room and Zoom. So, back, yes.
So, can you go back to the penultimate figure, the previous figure? Go back one slide. Here.
This one?
Yes, I'm curious if you can say a little bit more about how you date the time at which each of these events might have merged with the Milky Way overall.
So in fact, this is not my work actually. This is actually based on a comparison of the population of global clusters around the Milky Way to numerical simulations where star clusters form. So cosmological simulations that include some form of recipe for cluster formation, and where people have done some training through a neural network. So this is very dark way of characterizing when these objects fell in, I find particularly. I would like to do this on the basis of the ages of the stars. But I don't think we're that far from being able to do that now that we went through all this trouble of fitting isochrones, right, to each one of these objects. So what we have is an average age to this object. And so what we can do, at least as a first step, is to say, okay, what is the average age, and plot against an estimate of what the mass of the object is, and construct really on the basis of stars a merger tree like this one that I showed.
That tells you when the stars. That tells you when the stars formed, but it doesn't tell you.
Yeah.
When they're not. And those are not quite the.
No, indeed. And there are for at least one of the objects, for example, the Helmi streams, there is an asymmetry in the distribution of stars in velocity space. If the object is fully phase mixed, you don't expect it to be there be an asymmetry in velocity space. So the asymmetry can be used to date when the merger happened, and it's something like 6 gigayears ago, but the stellar populations are not younger than 10 gigayears old. So there is indeed that uncertainty, and I think I think a first step is at least to use the ages that we can derive. At least that might tell you when star formation was truncated, when it was quenched. If it's interesting if there is a mismatch between the dynamical age that you would infer, which you could try to model with embodied simulations, and the age of the stars. I think that would be particularly interesting.
Okay, we'll have a question from Bruce Strain on Zoom.
Thank you for a great talk. So question is 2 parts here. The first part of my question is the Gaia-Enceladus merger event. What amount of gas do you think came in, and what would be the consequences of mixing, low or negative angular momentum gas infalling with the gas that was already in the disk? Whether that would show up have a signature. The other half, the related half of the question, is Nissen, Christensen, Dalgaard et al. Last year had a very interesting paper where they studied the metallicity of solar type stars as a function of their ages based on accurate modeling of the stars, masses and ages, and concluded that there was that stars 7 billion years old had metallicities that were higher than solar abundances. Stars 6 billion years old had metallicities lower than solar abundances by about a factor of 3 change in metallicity, as though there was a large influx of low metallicity gas into the interstellar medium about 7 billion years ago. That seems a little bit later than your merger event, but I'm wondering are there any signs of such things? So thank you.
Yeah, thanks for the question. I think it would be hard. It's hard to constrain how much gas such an object would have. But the smaller the galaxy, the more gas rich it is, right? So at least in the simulations from the Eagle suite, I think the 50% of the baryons are in gas. So these are rather gas-rich systems. Now, what is interesting, I think, is, and I still haven't been able to make sense of this, but if you look at this sequence, if you look at the most metal-rich stars, they kind of have the abundance of the thin disk. So I find that a bit of too much of accidents, but I don't know enough to say, maybe this is, there is a reason for this. That the gas is, in comparison to the amount of gas that the Milky Way had, I don't think this was very significant, but it could have definitely lowered the average metallicity of the gas that was present at the time. With respect to the other study, there's another accretion event that's going on, and that is with the Sagittarius dwarf galaxy. And that accretion event probably started, this object is still being disrupted, but that probably started somewhere between 6 or 7 gigayears ago. So I wonder whether that is the reason for this lower metallicity population. There's evidence that Sagittarius has had an impact on the disk from the star formation history. So perhaps these things are related.
Thank you.
Thanks for a beautiful talk. I wanted to ask you if you think it might be possible if the Enceladus was a sort of composite object that's, composed of, say, a couple of different mergers. The reason I'm asking is the mixing argument that you're pointing to that suggests its age of, not exactly, but an old age. I've heard recently that it could be younger, it could be maybe a composite object. So that's sort of the background for my question.
Yeah. So I think there are a number of reasons why a composite object doesn't work. The first one is a mass metallicity relation. So the fact that you see a sequence, this chemical sequence, the slope of this sequence tells you kind of the star formation rate. You can integrate that gives you a mass. The fact that this object has a relatively high metallicity means that this object was relatively massive. And if a massive object comes in onto the galaxy, then it will do something to the galaxy as we see it. So I think there's an issue there on, say, what are the masses inferred from the chemistry and the timing of the event. In terms of the velocities of the stars, we don't really see a lot of asymmetry. So we don't see asymmetry in fact. So the degree of mixing, this object has really well mixed. So it cannot have been an object that has fallen in recently in that context, also dynamically. Now, could it be more than one object? I think the scatter in the, if maybe there's another, there's a better plot showing this. I think the scatter in the, say in the metallicity distribution, at least at the high end, is relatively narrow. So I don't think many objects can do that together, right? You would have to have some kind, they would typically follow a different sequence, like you sort of see, for these objects. It could have fallen in with other objects, right? So this could be the big thing, and then it brought in other satellites. And that's not inconceivable. But I think the structure here as is, it doesn't look like it is composed by several different objects. At least from the study of the clustering, the study of the populations, we don't really see differences.
Eve on Zoom.
Yes, thanks for the very nice talk, Amina. Can you go back to your slide 13? I think I have questions related to both of the questions about star formation in the thick disk and the how you date this age. I think this is the right one, because here this is the ages of stars in the red sequence, and the
yes.
Okay. So those stars already existed, and then you don't feel confident about when this event occurred, essentially, because I think I earlier misunderstood this as this is the date of the merger, but
no,
I think that, so we shouldn't take this as a time delay I mean, I think that there couldn't possibly be a 2 gig-a-year time delay between the event and this, between the merger and the thick disk forming. So you're saying that,
no. All I'm saying is that what you see is that, the object didn't form stars after it was disrupted, basically, right? So this tells you when it fully merged, kind of.
Okay.
And
so
what
then
you
the
see is
thick
that
disk,
around that time, you see a burst in star formation, but it doesn't mean that there weren't any stars forming here.
Okay, great, thanks. But I mean, is this is basically my related question is the only way you can tell the age really based on looking for events in the disk itself rather than in the, the evolution of orbits in the stream?
Yeah, so these are different ages, right? So one is a dynamical age and one is from the stars, and the two don't need to match, like I was saying, and they don't match in some cases. We haven't tried to age date on the basis of the dynamics because I think it's rather complex because it might be model dependent.
Okay, thanks.
I'm intrigued by your 7 what you call disrupted clusters, and I'm wondering if there are any theoretically motivated or observationally motivated ways to distinguish between disrupted clusters and infalling ultra faint dwarf galaxies.
I think the scatter in the one way, at least for me, would be a scatter in the metallicity of the stars, right? So if it were a star cluster, basically all of the stars would have the same metallicity. If it were an ultra faint, then you would say you can have a spread in metallicity as people find for the ultra faint. I think the dynamical size, I'm not sure would be so revealing because this would have very small velocity dispersions to start with in both cases. One perhaps slightly more extended. So it could be that by doing some dynamical modeling, you could tell one from the other, but I think it will be mostly from the star populations that we'll be able to say what it is are. Excuse me.
Before I go to the next one, how long do we go for?
Maybe just another one.
Couple more?
Just one or two.
Okay, let's have one from Zoom and then we'll have one in the room. So last one from Zoom, Amitabha again.
Thank you. I was returning to the question I asked you during the talk and just wanted to say that I really liked the way you organized the data according to the energy angular momentum conservation laws. That does reduce the size of phase space to 4. And what I was wondering is, you didn't show any plots where you say looked at ZVZ to figure out whether there are any oscillations there. I saw an interesting paper by Antoia, Nature 2018, which seems to suggest that these are there, but I was just interested in looking at your data, given that you have this conservation law information and what we could learn from that as a possible test for n-body simulations.
Yes, thanks for the question. So in fact, I was co-authoring the paper from Antoia on the spiral. So this oscillate. So you see this kind of a spiral pattern that is an indication of phase mixing. Now, if you wait long enough, the pattern becomes more and more compact, and at some point, it's very hard to see the individual wraps of that pattern if you wait long enough. And for many of these objects that have been accreted a long time ago, I think it will be very hard, particularly in ZVZ, to see a pattern that you could then use to basically establish when this object fell in. Even though it should be there, it's just it will be almost coarse grained. The errors are likely too large to be able to see this. It should be there. I mean, we're seeing streams, and the streams are simply a reflection of there being, this phase mixing going on. In the case of the pattern from Antoia, it seems to be something that has arises from a perturbation that happened roughly half a giga-year ago. So it's relatively recent, and it's a perturbation on the thin disk. So these are stars on very cold orbits, and that's why you can see the pattern still. But there should be many such patterns also from perturbations from earlier times. And I think people are looking into this, to looking for patterns elsewhere in the disk to try to see if they can constrain, say, other perturbations in the disk.
Thank you.
Do we have one final question from the room? Yeah.
Thank you for the great talk. And can we go to the figure that shows the several groups and with different hierarchy?
Yes, the dendrogram. Let me see. This one? Maybe?
Probably the previous. This one. So I can see it seems that there are like many groups and subgroups, like this kind of hierarchical things, and I'm wondering if this is physical, or for example, can that be due to like some global cluster coming with the satellites, or there's some other physical reasons for this hierarchical structure?
Yeah, that's a very good question. We don't know yet. There could be a physical reason, which could be related to each one of the streams that crosses the solar volume. So a stream is basically a group of stars that are on an orbit that have a very similar phase. And so let me show you again this plot. Oh, sorry about this. I think my PowerPoint collapsed. Give me just a second. If I can restart this again. So it could be related. What I was saying is that it could be related to the different streams that are crossing the solar volume. So if you look here, basically, this is not so clearly seen here, but basically what you get is you can get substructure within each one of the clumps associated to the different streams that are crossing the volume. So this would be one explanation, but there is another explanation. There are other explanations, and I don't think we are resolving all of the streams that are crossing the solar volume. And the other explanation is it's a dynamical origin, and I'm going to discuss this in the lunch talk. But at least for one of the structures where we see splitting due to a resonance in the orbit of the stars, and that introduces a splitting of a large clump, and yeah, so it does have a physical origin. What I don't dare to say is whether it's all related to such types of streams or resonances that are affecting the motions of the stars, such that you find these clumps. Some of these might be structures within the original object. I think these are things we need to explore further to be able to say, what is the physical reason for this.
Okay, with apologies to those people who still have questions, let's wrap up there, and let's thank the speaker one more time.